Data collection began as a physical process of manual entry and hardware-bound storage. To process this information today, we must first translate those physical observations into a framework of mathematical abstraction. We will build that framework by starting with the logic of sets, then moving through linear geometry and quadratics until we reach the high-degree polynomials used in complex data fitting. Our variables exist within a nested hierarchy of number systems. We begin with natural numbers and integers, then expand to rational numbers, which we simplify using the greatest common divisor. By including irrationals, we complete the set of real numbers. In this system, arithmetic operations are precisely defined. We rely on the modulo operation to calculate remainders, and we use factorization to identify when one value divides another exactly, resulting in a modulo of 0. We organize these values into sets, well-defined collections of items. A set can be finite or infinite, and we measure the total number of distinct elements it contains as its cardinality. When every element in set X is also found in set Y, X is classified as a subset. If Y contains additional elements not found in X, then X is strictly defined as a proper subset. To automate the creation of complex subsets, we use set comprehension. This utilizes a generator to pull from a source set, a filter to isolate elements, such as even integers, and a transformer to square or modify the final output. Establishing these discrete sets is a required step for modeling. Before we can analyze a relationship or predict a trend, we must first define the mathematical boundaries of the data itself. Once our sets are defined, we can describe how they interact through relations. Mathematically, a relation is a subset of the Cartesian product, a collection of ordered pairs where one element is drawn from each set. If a relation is reflexive, symmetric, and transitive, it satisfies the requirements of an equivalence relation. A function is a more restricted form of relation. It requires a mapping where every input in the domain corresponds to exactly one output in the codomain. Within that codomain, we identify the range, the specific subset of values that are actually produced by the function. We further classify functions by their mapping behavior. An injective, or one-to-one function, ensures that every input maps to a distinct, unique element in the codomain. A surjective function is onto, meaning the range of the mapping is exactly equal to the codomain. If the function is both injective and surjective, it is classified as bijective. Defining data relationships as functions provides the mathematical predictability needed for analysis. It ensures that a known input will always yield a single, consistent output. To visualize continuous data, we move from sets into the Cartesian coordinate system, organizing the plane into 4 quadrants. Here, we measure distance between any 2 points by calculating the horizontal change in x, the vertical change in y, and applying the Pythagorean theorem. Using the section formula, we can locate any specific point along a line segment at a set ratio, whether it falls internally between the points or externally beyond them. We can also calculate the area of any triangle formed by 3 sets of coordinates. If the area is exactly 0, we have mathematical proof that the points are collinear. The orientation of a straight line is defined by its slope, m.
Algebraically, this is the ratio of vertical change to horizontal change. Geometrically, it is the tangent of the line's angle of inclination. Slopes also define how lines interact. Parallel lines possess identical slopes, while perpendicular lines have slopes that multiply to exactly -1. We express these linear relationships through 6 standard equations: general and slope point, y-intercept and x-intercept, intercept, and 2-point forms. When lines intersect, we calculate the specific angle between them by comparing their individual slopes. We can also define the shortest distance from an independent point to a line, or the constant distance separating 2 parallel lines. This chart shows a scatter of data points and a linear model of fit. To measure its accuracy, we calculate the sum-squared error. We measure the vertical distance from each point to the line, square those values, and sum the results. This calculation condenses all deviations into a single value. By iteratively adjusting the line's slope and intercept until this error sum is minimized, we find the most accurate linear approximation of the dataset. To model nonlinear changes, we use the quadratic function, where the variable is squared and the leading coefficient is non-zero. Its geometric representation is always a parabola. Every parabola has a vertical axis of symmetry intersecting a unique vertex. Its concavity depends on coefficient a. A positive a opens the curve upward with a minimum vertex, while a negative a opens downward, creating a maximum point. Unlike the constant slope of a line, a quadratic slope changes at every point. This instantaneous slope is calculated as 2ax plus b. We locate the curve's x-intercepts by solving for its zeros. This is done through factoring, completing the square, or using the quadratic formula. The quadratic formula includes the discriminant, the algebraic term b squared minus 4ac.
Its value determines the curve's roots. Positive means 2 real roots, 0 means 1 root, and negative means no real roots. By identifying roots and the vertex, quadratic models mathematically locate the exact points of maximum output or minimum loss within a nonlinear dataset. For data with multiple fluctuations, we use polynomials. These are algebraic expressions consisting of addition, subtraction, multiplication, and variables with natural exponents. We classify polynomials by their degree, the highest exponent in the expression. As the degree increases from 2 to 3 or 4, the function gains the mathematical capacity to change direction multiple times. We perform operations on these equations by distributing and combining terms that share the same degree. Polynomials can also be divided using long division. This structure breaks the expression into a divisor, a dividend, a quotient, and a remainder. High-degree polynomials share specific geometric properties. They are always continuous, meaning the curve never breaks, and they're always smooth, with no sharp corners. Solving for polynomial zeros identifies where the function intersects the x-axis. If a value a is a 0, then x minus a is proven to be a structural factor of that polynomial. This progression, from discrete sets to n-degree polynomials, establishes the formal language needed to describe data behavior. These algebraic structures provide the necessary framework to translate raw observations into the predictive functions used in modern modeling.